Okay, I should be unmuted now. So this is for chapter 27. I have a few up here. So we'll do chapter 27. It's actually the 15th now. And this chapter deals with magnetism. One of the main rules that you learn is called the right hand thumb rule. So even before we start with our problem, we're gonna go ahead and write that up here in the corner. And so it's saying that, like, if you had your right hand thumb, you had your fingers curled around like that, then the way direction that your fingers are curling is your magnetic field. The direction that your kind of knuckles are going in is the V, or particle velocity. And then the way that your thumb is going is the current direction. Would be I. I guess I should probably. Okay, let's see. I am on my iPad, so we'll see if this video works. Okay. So you got your hand, right? I know this is probably on like Zoom, so this is my left hand, this is my right hand. So right hand, I go, okay. My thumb is going up, that's gonna be my I. My fingers are gonna curl this way, which means that's gonna be my B, the direction that my fingers are curling. And then kind of the way that my knuckles are going, or like before I curl them, so it's before I curl them, right? That's the direction of the V. Then after I curl them, that direction of, oh, I am not in that direction of curling is the B. Let me just stop share. That way I can see it big here. Somebody's not letting me. That works. That also works with FBI. Anyway, your B is still gonna be your direction of curling. But this time, like, it's gonna be your F that's going up and your I that's going with your thing. And then if they draw like an X on the paper, that means that if it's like an arrow, it's kind of coming into the page. And if you see like a dot with a circle, then it's going out of the page. I actually have. Right. Because if you have an arrow, it's saying the direction of your travel, right? And then if you have, say, an arrow like this, if it's coming into the page like this is not a straight arrow, but you have like a dot with a circle around it. Versus if it's coming out of the page, so like if you're the page and this arrow is coming out, like you're gonna see just the kind of X. I know it's not really an X, but you're gonna see the back of the arrow. Right? So it's what you're gonna be seeing if the arrow was like moving in or out of the page. Let me do it this way. Okay, so I have a paper, right? So if the arrow here is coming into the page like that, then you as a viewer, you're gonna view like this, right? Because that's the arrow is going into the page. You're seeing the arrow go into the page. Versus if you're seeing the arrow come out of the page, so say that this is like coming out of the page here, then you're gonna see that dot with the circle. So I just remember that's something that I always had trouble visualizing. And then again, we have the right hand rule where we have I going up, our V going in the direction of our hand being straight, and then our B going in whatever direction it's curling in, right? So it's like a thumbs up, but curling, direction of your knuckles, and up. Now let me go back to sharing content. Anyway, yeah, we'll just start solving now. So we have a wire that carries a current. We have our current here and has a given length. And then you have a angle that the magnet is, or where the pole is in reference to the magnet, between the pole faces of a magnet. And the field is approximately uniform. We ignore the field beyond the pole pieces. Okay. So if we were to draw this, so we have a wire, which is 18 centimeters long. Between the pole faces of a magnet and then the magnetic field. Let me draw this straight up and down. And then we're asking the magnitude of the force on the wire. Oh, okay, I don't think you need to draw for this one. Because it's asking for just the magnitude of force, not the direction of force. So that means we can just use one of these up here. We have I there, which is current. We have our L here. And we have our B here, along with our theta. So we're definitely going to be using this equation here. So force, that's going to be our force. It's equal to IL B sine theta. And then I think this is just plugging it all in. So 45 angstrom. I would probably change this into meters just to be safe. So 2, 1, 2, 0. And then our B. Okay. And then angle. If we go ahead and plug that in, we get 0.3 sine 50. I got force is equal to 1.86. We are going to double check the units right now. We know that force should be like newtons, right? This here means Tesla. Here's angstrom, which we saw in our last kind of chapter. And then that's meters. I don't think she ever gave us the breakdown for Tesla, huh? I don't see it anywhere in my notes. Yeah, once you get up to magnetism and stuff, it's harder to use your units to double check yourself. So I guess just know that those are the units. And then it is force, so it's supposed to become into newtons. And then we have a magnetic field that's exerting a force. We have our force here towards the east on a proton. That's moving vertically downwards. Okay, so let's focus on the proton first. So we'll have the proton. The proton. It's moving vertically downwards. So that's direction of motion. And that's going to be V. And then we're given our V, so we're just going to go ahead and write it in. And then we have a magnetic field that's exerting a force on this. So towards the east, right, we have never eat soggy waffles. Where we're assuming downwards is south, I guess. But in that case, the force is going to be coming from this side, right? Because it's heading towards the east. So it's going towards the east. We're going to have force there. We're going to be... That's going to be 5 times 10 negative 14 newtons. And then determine the magnetism direction of the magnetic field. And we're given the charge of the proton. Okay. Let's start by the magnitude. We're also given the charge, so that should be probably this equation up here. So now BF is equal to QVB sine theta. I believe because we do have sine theta, it's probably going to be this angle right here, which is going to be 90 degrees. Our Q is given here. Our V is given here. And our force is given. So we're solving for B. So we go ahead and isolate for B. Which is going to look like just dividing everything else out. Pretty sure this sine theta is going to become 1, but we're going to plug it in and just make sure. Sine 90. Yeah, according to my calculator. So then we have B is equal to over Q coulombs and velocity and then 1 because the sine theta is equal to 1. That's going to give us 6, 19, 8, 6. I got 0.039, and I'm pretty sure that's supposed to be Tesla's. You know what? Let me just look up the unit for Tesla. Okay. So Google is equal to a variety of things, such as volts seconds per meter squared, newtons seconds per coulombs meter, kilograms per angstrom second squared, which is probably why I never was able to figure it out. But using that sort of stuff, there's more, but those are all the ones I'm gonna write right now. We'll figure this one out up here. We have angstroms times meter times, I'm gonna guess it's gonna be this kilograms per second squared over angstrom second squared. That would get rid of these two, which would give us meters over second squared, kilograms, which is newtons. Right, because that's acceleration in mass. So that checks out. That's good. And then down here, we'd probably be using the newtons seconds, this one. So that one's going for that one. And we'll use this one for this one. Because in this case, we have newtons over coulombs times meters over seconds. That becomes newtons over 1 over coulombs times meters over seconds. You can group those together, and that's going to give you newtons seconds over coulombs per meter, which, hey, that's our units of Tesla, which is good. That works out because that's for magnetic field. Cool. So we have our magnetic field magnitude. Now we need to figure out the direction. We have our first right-hand rule. So let me turn on the video at least. Okay, here we go. Come back over here. Okay. So we have our force, and it's coming in this way, right? And we know that for the right-hand rule, there was the IVB version and the FBI version. And for the FBI version, the force is your thumb. So we're saying the force is coming in this way, right? We don't know we know our I. We should know our I. How do we know our I? We know our I because it's the same as the velocity, right? Because in this case, we have a proton, and it's going with the velocity. So it's either going to be like this and curling like this. So we have our velocity going downwards, our force going this way, which is going to make our fingers curl like this. So, right, this is the page. Oh my gosh. The iPad is fighting with me. It's trying to keep me in the center, but I'm trying to show you guys my hands. So force velocity is curling in this way. So that means that the magnitude or the magnet is coming around this way, like this. But in this instance, it looks like it's coming out onto you. So because it's coming out, it's like your fingers are pointing towards you. So it's coming out of the page. So you're going to draw it like it's coming out the page. And if you imagined it was like an arrow, if it's coming out of the page, then you're going to see like the point of the arrow. So it's going to look like this. Right? Because it's kind of coming like this out of the page. I don't know, it's hard to draw. It's like going into the page and out of the page. And then you have your magnitude here. Cool. Anyway, I know this was kind of short, but I don't think you guys covered this chapter all too much anyway. So it should be okay. Because yeah, those are the only two problems that I have for practice. So yeah. Good luck and take care. Bye.